Now we arrive at PPO, and to motivate it you have to see what still goes wrong. With plain policy gradients, one update that is too large can be catastrophic. The policy lurches, and suddenly the data you collected under the old policy no longer describes the new one. It is stale. You make a confident move in the wrong direction, collect biased data that confirms it, and performance can collapse and never recover. We want to take useful steps without ever taking a reckless one. The first ingredient is important sampling, and it solves a practical itch. We would like to reuse a batch of data for several gradient steps instead of throwing it away after one. To do that correctly, we reweight by the ratio of the new policy probability to the old policy probability for each action. That ratio, written R of theta, is 1 when the policy has not changed and drifts away from 1 as it does. The surrogate objective is just that ratio times the advantage. But left unchecked, that ratio is exactly what lets an update run away. So PPO clips it. The clipped surrogate objective takes the minimum of two things, the ratio times the advantage, and a version where the ratio is clamped to between 1 minus epsilon and 1 plus epsilon, again times the advantage, with epsilon usually 0.2. Taking the minimum means we always trust the more pessimistic estimate. In plain terms, the objective stops rewarding the policy for pushing an action's probability too far in a single update. That one line is the whole proximal idea, a trust region enforced by a clamp. The notebook plots exactly how the clip behaves, and it is asymmetric in a satisfying way. When the advantage is positive, a good action, the clip caps the objective from above once the ratio passes 1 plus epsilon, so you cannot get greedy and over-promote it. When the advantage is negative, a bad action, the clip caps it from below, so you cannot over-punish and slam its probability to nothing. Either way, once you have moved far enough, the gradient flattens out and stops pulling. That is how a simple minimum gives you a soft trust region for free. The full PPO loss has 3 parts. The clipped policy objective, a value loss training the critic toward the returns, and an entropy bonus, a small reward for keeping the policy uncertain so it does not collapse onto one action too early. And because important sampling lets us reuse data, PPO runs several epochs over the same rollout, recomputing the ratio each time. 2 more details that matter: it normalizes the advantages before the update, and it clips the gradient norm. Skip the advantage normalization, and PPO gets noticeably shakier. This is the question interviewers love: why clipping instead of a hard KL constraint? Its ancestor, TRPO, solves a constrained optimization, maximize the surrogate subject to the KL divergence between old and new policy staying under a limit. That is principled but expensive. It needs the natural gradient, conjugate gradient, and a line search, hundreds of lines of finicky code. Ppo's insight is that the clip achieves a similar trust region effect with nothing but first-order gradients and standard atom. It is far simpler, plays nicely with normal deep learning tooling, and empirically performs just as well. That simplicity is why PPO won. What if you skip the clip and just use a bigger learning rate? You get policy collapse, and the notebook walks the exact death spiral. A large step makes the policy overconfident about a few actions. The next rollout only samples those actions, so the data is biased. The gradient computed from biased data reinforces the same overconfidence. Round and round until the policy is deterministic, stuck on a suboptimal choice, and can never explore its way out. The clip prevents step 1. It limits how far any single update can move an action's probability. Now the payoff, why this notebook is the gateway to RLHF. Map the pieces onto a language model. The state is the prompt plus the tokens generated so far. The action is the next token from a vocabulary of tens of thousands. The reward is a reward model score, handed out at the end of the generation. And a KL penalty against the original supervised model keeps it from drifting into gibberish. Clipping matters even more here, because the action space is huge and tiny shifts in token probabilities can swing the output, so stability is everything. This is precisely why OpenAI used PPO, not TRPO, for instruct and chat. The production notes draw the gap between this notebook and a frontier lab. Here the environment is cartpool, 4 numbers and 2 actions. There it is language generation, a vocabulary in the tens of thousands at every step in episodes that run hundreds of tokens. The value function is no longer a separate toy network. It is an extra head bolted onto the language model's shared backbone. And you run fewer epochs per batch, just 1 to 4, because too many overfit the small batch of generations. Same algorithm, wildly different beast. Here is the honest warning. PPO is notoriously simple to get wrong. It has around 10 hyperparameters that interact nonlinearly: learning rate, clip epsilon, GI lambda, epoch count, batch size, value coefficient, entropy bonus, gradient norm, and more. There is a famous blog post cataloging 37 implementation details by Costa Huang, where subtle bugs cause 2 to 3 times performance swings. The usual suspects: computing the advantage in the wrong order, botching reward normalization, or forgetting to reset state. And PPO is so seed-sensitive that serious runs use multiple seeds and aggregate. Since it breaks quietly, you watch a few dashboards. Clip fraction, the share of ratios getting clipped, wants to sit around 10 to 30%, above 50 and the policy is moving too fast, below 5 and it is barely learning. Explained variance of the critic should climb over training. Low values mean your advantages are noise. Entropy should drift down gradually. A sudden drop is premature collapse. And the approximate KL between old and new policy should stay small. Many implementations use it as an early stop for the epoch loop when it spikes. In interviews, this shows up as a derivation, 15 to 20 minutes at the whiteboard. The expected arc is the one we just walked. Start at the policy gradient theorem and reinforce. Add a baseline and justify why it stays unbiased. Introduce important sampling. Then land on the clipped objective and explain why the minimum gives a pessimistic bound. A senior candidate writes the objective and explains clipping and GI. A principal candidate derives it from first principles, connects clipping to the trust region and the Fisher information, and can argue when PPO fails and whether simpler methods would do. One more thing the notebook is honest about: PPO is increasingly replaced by simpler methods for alignment, direct preference optimization, group relative policy optimization, and KTO. But understanding PPO deeply is still expected, because it is foundational, because reasoning models still use PPO variants, DeepSeek's GRPO for instance, and because it tests your reinforcement learning fundamentals like nothing else. The depth signal is being able to say when PPO is still preferred, when you need online exploration, reasoning tasks, or process reward models. So here is what you can now do. You can tell the whole story, from reinforce and its variance problem to baselines and why they stay unbiased, to actor critic and the GI dial, all the way to Ppo's clipped objective and why it beats a hard KL constraint. You know the failure modes, the knobs, and the dashboards that tell you it is working. And you can map every piece onto a language model, which is the doorway to RLHF. Follow along on the frontier path, where Moot studies the machine learning interview in the open.